In the last video, I talked about how it is possible by adding some impurities to silicon to either make it more conducting, and that there were two ways to do it. One is by adding a type of impurity that provides extra electrons, and these extra electrons can go into the conduction band. The other type is an example of that would be phosphorus. The other type is by adding impurity that would remove electrons from the valence band, thereby making it not fully occupied, and therefore it can then conduct. An example of this type of impurity would be aluminum. Now, before I go on to describe how this is used to make a PN junction and a diode that is useful for electronics, let me just emphasize again that if these impurities not been added, then semiconductor, like silicon, has a band structure in which the valence band is fully occupied and the conduction band is completely empty. Okay, and it is only the small gap, the small energy gap between the two bands that would allow some electrons to be excited from the valence to the conduction band by thermal energy, by maybe silicon atoms colliding with each other because of the temperature. But these electrons that get excited, only a very small amount would get would happen, or would get excited to the conduction band. So although it can conduct a little bit, it would be a very poor conductor. In other words, if we just use silicon itself as a conductor, it would have a very high resistance. Right? So it would be a very, very poor conductor. Whereas the moment you add these impurities, like either aluminum or phosphorus, it would become a lot more conducting, a lot more. Okay, so let me now talk about the PN junction, which can be used as a diode that allows current to flow only in one direction. Call that the N. Let's say this is the N-type semiconductor, and that is the P-type semiconductor. So this one has impurities that provide additional electrons in the conduction band and helps it to conduct. This one has impurities that remove some electrons from the valence band and help that to conduct better. And the idea is that we can pretend that those holes are like positive charges, like electrons with positive charge. Okay. But first, let me take a look at what happens when these two types of materials are placed side by side. Right. Now, because let me just start with this one, for example. Because this has these additional electrons in the conduction band, these electrons in the conduction band can diffuse over to the p-type semiconductor. The electrons from here can diffuse into here, and when it does so, it will fill up some of the holes. It will fill up some of the holes in the p-type semiconductor. So let me draw some electrons here to show that. So the electrons from here diffuse into here, and it will fill up some of the holes. Write that out. Fill up some holes. Okay. Now, coming back to this N-type semiconductor. Now, there's one point that I should emphasize. Now, before the electrons diffuse into here, the electrons, what I describe as additional electrons that go into the conduction band. Now, the fact that there are these additional electrons that go into the conduction band doesn't mean that this N-type material as a whole is negatively charged. Okay, it doesn't mean that. This N-type material as a whole is neutral. It's just a neutral material with and every atom on its own has the same number of protons and electrons. So we're talking about neutral atoms here, but they're combined in such a way that some of the electrons from the impurities can go into the conduction band. Okay, as a whole, it is still neutral. So if some of these conduction electrons can diffuse into the other side, the other type of material, then within this N-type material, it means that it has actually lost some electrons as a whole to the other side. It has lost some electrons to the other side. That means that this N-type material must now become positive. Before it is neutral, and now it has lost some electrons, so it becomes positive. So it must now have positive charges, and it does. And these positive charges would be sort of around here. All right, they would be around here, simply because they would be attracted by the negative charges that has gone over. Okay, so these like I said before, we can pretend that the holes are positive charges. So when the electrons from the N-type goes over to the other side and fill up some of the holes, okay, although it has filled up the holes, and we can think of the holes as positive charges, it doesn't mean that the presence of holes would make the p-type semiconductor positive. Right? The p-type is still neutral as a whole. The holes just means that there are empty spaces in the valence band. Okay, it doesn't mean that this whole piece of thing becomes positive. So therefore, if there are some electrons from outside coming into here, this has to become negatively charged. Okay, so once we are quite clear about this, there are actually negative charges here, and there are actually positive charges here. Okay, and they will attract each other. So the negative charges from the electrons from the N-type semiconductor will diffuse towards the positive, the p-type, because there are more electrons here than here, so it will diffuse over. Okay, that's how diffusion works. Particles diffuse from higher to lower concentration. So there's this tendency, this diffusion tendency. Okay, so you will try to keep diffusing more and more to the other side, but as it diffuses, you gain negative charges here and positive charges here, and like I said, they attract each other. So the positive charges here will try and pull the negative charges back. So we have two forces here. we have what looks like two forces here. We have this diffusion that tries to go to the left, and we have this electric force that tries to pull the electrons back. So at some point, the two forces would balance, and we would have a kind of equilibrium where there's a certain amount of negative charges here and positive charges here, and then the amounts will not change after that. Okay, this will still try to diffuse to here, but it would be continually pulled and balanced by the attraction. Okay, so what happens then is that we would have a certain layer here, a layer of a certain thickness of negative charges here and positive charges here. Now, one important point about this layer here, is that because the holes here are filled up, and because the negative charges in the conduction band here has left and gone over to the other side, this region is no longer a good conductor. It's no longer a good conductor. This region becomes like just pure silicon, a semiconductor, very slightly conducting, but not a good conductor at all. Okay, so this region now has neither holes because it gets filled up here, nor electrons because it has diffused. Those have diffused over. So this region, which does not have this, if you like, mobile charges, or mobile carrier of the charges, is called the depletion region. In other words, the holes or the electrons that can carry electric current easily, they are depleted, right? They are not present anymore. They've like cancelled each other out. So there is this depletion region here, and this is a region. This is a region where there is the conductivity is very poor, right? This is the depletion region is a very poor conductor, and that means it has a very high resistance. Right. Okay. So now, so this is the understanding right now. Whereas the rest of the N-type material and the rest of the P-type material, they still have the carriers, meaning the rest of the N-type still have the electrons, and the rest of the P-type material still has the holes. So these two parts here are still good conductors. Okay, so this part here is still and this part here, they are still good conductors. Okay, so good conductors, poor conductor. Now, so let's see how this situation can be used as a diode. Now, if you recall, a diode is a device that can allow current to flow in one direction but not in the opposite direction. So how is this possible in this setup? So let's try pushing some current through this. Okay, let me draw this here again. Right, what I'm going to do now, okay, is I'm going to connect a battery to this. I'll connect a battery to this so that this side is positive and this side is negative. So I might have a battery somewhere up there, and I connect the positive pole to here and the negative pole to that. For example, okay, for example, if I just throw a battery there, this connects to here and this connects to there. Yeah, plus and minus. So what would happen if I do this? Let's think about what would happen to these charges here and therefore to the depletion region. So at first we have these the positive and negative charges. Positive charges here because electrons have gone over to here. Okay, so that's the initial starting situation. Okay, before I connected the battery. Let's think about what happens now that when we have connected the battery. Now this is a positive pole. This is positive pole, and we have here the n-type. We have the n-type material. Okay. Now the positive pole here means that let's see. Okay, there are the n-type material has extra electrons as in the which goes into the conduction band. All right, so this it has electrons that can carry current. Right. So if this is connected to the positive pole of a battery, it means that these electrons will be attracted to move to the positive pole. Okay, these electrons will be attracted to move out of the n-type conductor. So if electrons flow away, if electrons flow out, this means that there will be fewer electrons here, and therefore there will be even more positive charges. There will be more positive charges, and the positive charges would accumulate towards the left, towards this side, because we can think that it gets repelled, either repelled by the positive pole or attracted by the negative electrons there. But in other cases, electrons flow out, the remaining positive charges would just accumulate towards the left, towards this depletion region. Now we might imagine that on the other side, something similar happens. Maybe opposite in charge, but quite similar. See, you have a negative pole connected to here. So this means that electrons will try to flow in to the p-type, to this p-type material. Now as electrons flow in, it will start filling up the holes in this material. And as electrons flow in, it will gain negative charges. So these negative charges, right, as it flows in, will be forced towards the right, because this is a negative pole. This is connected to the negative pole, and the negative pole would repel the electrons towards this direction. So this means that there would be extra electrons coming in and accumulating on this side. Now if you take a step back and look at this and compare it with this, you see I describe this part as a depletion region. Okay, because the holes that get filled up, the electrons there has diffused away. Depletion region in which there is no or hardly any charges that are free to move. Now, if you compare this picture with this picture, clearly the depletion region here has become wider. Okay, so this depletion region has become wider. Now, and this just means that, as I described just now, the depletion region is a very poor conductor. It has a very high resistance. This means if this region becomes wider, it just means that this setup, this whole thing here, becomes an even poorer conductor. So it's even harder for an electric current to flow through if you widen the depletion region. So wider means even higher resistance, so even harder for current to flow. So we have here a situation in which very little current will flow. Okay, if you connect the battery this way, very little current will flow. Now let's look at what happens if I connect the battery the other way round. Draw it down here. So this is the N-type. A little bit bigger. This is the N-type, and this is the P-type. This time, I want to connect the battery the other way around so that this side is plus and this side is minus. So what happens now? Okay, let's go through the exercise again. Right. In the beginning, I have minus and plus. Let me fill those in. Minus here and plus here. Now if I connect the negative pole here, then the battery will try to push electrons into here. So electrons will be attracted towards the positive charges here. So as electrons come in, it will cancel the positive charges. Now remember that this is N-type, meaning that it has electrons in the extra. It has electrons in the conduction band from the impurities. Okay, that can help it to conduct electricity. Electrons in the conduction band that can move. And but this part, remember, this part originally has got the electrons depleted because those electrons has diffused away. So this part has no or very little conduction electron before I connect the battery. But the moment I connect the battery, the negative charges here will come in here and supply this place with negative charges. Right? It will not only cancel the positive charges, it will supply this part now with electrons. So previously, the electrons there, the electrons that can carry current, the electrons there in the conduction band is diffused away. Now they get replaced. Now this part gets replaced by new electrons coming in from the battery. So the charges here are cancelled. Charges here are cancelled, but the important thing is that it has gained electrons. Okay. Now, and on this side, the positive pole will try to attract electrons away. So the electrons here, which has filled up the holes, remember it's the holes that allows you to conduct, because these are empty spaces in the valence band. These electrons here will be attracted away. So the holes there that were filled up and therefore gone, okay, is now would now appear again. So the electrons here, because the electrons here get removed, so we get holes there back. Okay, so basically down here, the electrons are replaced by what comes in here, and down here the holes reappear. So we now get the carriers back. We now get the charges, the mobile charges. We now get back the ability in this region to conduct electricity. Okay, so that the depletion region from which the carriers of current, the charges from which are the holes and the electrons that can carry the current, have been removed. This depletion region is now, in a sense, replenished. Okay, we put back in the electrons there that were removed, that has diffused away. We put them back in here, and the holes that got filled up, we clear them up again by taking away the electrons. So the holes reappear, the holes can carry current, electrons are replaced, electrons can carry current. No more depletion region, no more high resistance region. The electrons and the holes that can carry current has come back, and so therefore this now becomes together this becomes a very good conductor. Okay, right, so there we are. So now that it has become a very good conductor, therefore a current can flow. Okay, so the current can now flow through this, what is called a PN junction.